See right here that looks like an ordered pair is often preceded by GCD. Okay, GCD stands for greatest common divisor. Sometimes it's called the HCF also. A lot of people will carry this around. Most people these days, I think, in number theory textbooks, write it just as an ordered pair, and it's very context sensitive. So there's no ambiguity. You know, you're dealing with number theory here. You're not talking about an interval of real numbers. Okay, but we're supposing that two integers a and b don't have any common factors. That's what this means. The greatest common divisor of a, b is 1 means that a and b can't share any common divisors. Prime divisors or composite divisors either way. Now we're given this information that a and b have no commonality, if you will, and we're also given that c divides a, and c is another integer, and that d divides b. Now that means you can write a as, let me just write this, that's an a there, folks, sorry. A is equal to, we'll say c times c sub 1, and y'all like using these subscripts with the same letters. And right here, d divides b means that d is equal to, or b, excuse me. This would say that b is equal to d times, we'll say d sub 1. Okay, so again, that's what these two statements mean. Now we're trying to show that c and d under these circumstances will have a greatest common divisor 1, which makes sense. If a and b don't have anything in common, and if c divides a and d divides b, and a and b don't have anything in common, neither should c and d, just in a kind of a so-called common sense way. So now there's a famous result here that I won't spend too much time on, but let me just give you a concrete example. It's called Bezout's theorem, I think. And let's just look at a circumstance here. Let's say, I don't know, let's say what, 15 and 4? 15 and 4 clearly are relatively prime, meaning their GCD is equal to 1, okay? But what that means, there's a pair of, there's two integers such that, and you can just see this right now, you can write down what, let's see here, 15, you can write down 1 is equal to, and you know, you can, a lot of times you can do this by inspection. So what do we need here? We need 1 is equal to, we'll say 1 times 15. Let's say minus 1 times 15 plus 4 times 4. This is an example of what we mean by, I think that you pronounce it Bezout's theorem. In other words, the GCD of any pair of integers can be written as a linear combination, is what this says. A linear combination. There exist integers such that this condition occurs. All right. It's an if and only if also. I won't attempt to prove that, but you can see right here, x was -1 in this case, and 4 was y. Okay, and again, minus 1 times 15 plus 4 times 4 gives you 1. Okay, and if you can just make up any other circumstance like this, and if it happens, that means the two values are relatively prime. Okay, so that's just an example. Now let's get back to the proof here. This given right here implies the existence of two such integers, x and y. Okay, now also notice that based on our observations right up here, if c is a divisor of a, that means we can write a as c times some other integer, the same for b, all right? And so you can see exactly what happened right here. Okay, so a got replaced with what it's equal to, b got replaced with what it's equal to, and what do we end up with right here? Okay, we end up with, let's write this a little more carefully, c, and I'll put parenthetically, c1x, right? Which is just some other integer, right? Then plus d times d1y. You see, this implies, let me write the if and only if arrows, that CD is, the pair of integers CD are relatively prime, or coprime. So this is a fairly simple proof. You didn't have to use any, all you had to do is appeal to the definition of divisibility, and also this result right here that's famous from number theory. It can be, you can use the Euclidean algorithm. Right here, these numbers were small enough to where you could determine your x and your y. Again, this -1 would be your x here, and the 4 would be y. It's just coincidental that 4 worked. Normally, it's not the same as the integer involved. Okay, but anyway, we proved what we set out to prove. We just got another case of the Bezout theorem, where our integer was c1x for x. I mean, that's functions as the x, you know, the integer that exists such that this condition happens. These two guys right here in the parentheses played the role of x and y up here, and so that implies that c and d are relatively prime. Okay, so that's the end of the proof, QED. And y'all, I'll do another video fairly soon on the Euclidean algorithm and how it give you, right here, again, these were small enough to where we could identify -1 and 4 by inspection, giving us this linear combination that's equal to 1. Okay, but for larger numbers, it's not so easy. And there's something called the Euclidean algorithm where you can do it iteratively, and all the remainders are pairwise coprime or relatively prime. And then you get, you can run it all the way out. You finally get to 1, you know, or whatever your GCD is, and then you can do back substitution and actually determine these values of x and y by a method that's more algorithmic versus just guess and test. But anyway, that concludes the proof. Thanks for viewing.